Hello and welcome. In this lecture, we are going to be setting up a suspension type mechanism using our trusty physics constraint. So if we go ahead and hit play, you can see what I'm going to be creating in this lecture. There you go. That suspended mass on top is a lot heavier than the one underneath, even though they look the same size, and it's got the shock absorbed when it landed. And that's exactly the kind of behavior we want from suspension. So I'm going to show you how we can create this using a physics constraint, as well as explaining a little bit of the science behind a spring and things called oscillators and damping. And as a bonus, we're going to go into stabilizing our physics simulations and making sure that they don't glitch out on us. So lots to cover in this lecture. Let's dive in without further ado. Okay, so our ultimate goal here is to build a spring using this position drive. So what can we do to achieve this? Well, first of all, I've already kind of hinted at it. I said position drive rather than physics constraint, which is what I meant to say. So what we're going to be using is a feature of the physics constraint. So if I have my test constraint blueprint and I go into the physics constraint component and look at the details pane, you'll see there is a section in here called linear motor. And that's what we're going to be using to create this spring, basically. Now, particularly, we are interested in the position target element first of all. What this is saying is that it will try to move the constraint towards this position, or this position offset, because remember, this is kind of position 0 when they're both linked together. And the offset from that position we want to try and get towards. So you can enable any one of these in the X, Y, or Z constraint dimensions, basically. So I'm going to go for Z because we're going to do our spring up and down like a suspension. And then it enables this extra property called strength, and we'll see a little bit more about strength in just a second. But let's just try that out and see what that actually has created for us. We'll go ahead and hit play. Okay, it is still being limited by that limit that we've created in our constraint. Maybe if I free up the Z dimension, we're going to see something a bit better. Let's go ahead and hit play. And sure enough, we've got ourselves this spring with a really long travel. And it's obviously oscillating here as well. So that's kind of interesting. Why do springs oscillate? That's a question we're going to have to answer. But first of all, let's understand a little bit more about the theory behind springs. So there's a thing called Hooke's law, and I'll link you to this in your resources for this lecture. Hooke's law basically states that the force applied by a spring is proportional to its extension, and it obviously depends on the stiffness of the spring as to how much force is going to be applied. So that is the point here, and this is what's being shown in this diagram. We've got a spring at rest, a spring when you put a certain amount of mass on the end and it extends by x. If you put twice the mass, it expands by twice as much. That's basically what this equation is saying. F equals k times x. Funnily enough, this is exactly what's going on with our linear drive, our linear motor. With the position target, what it's saying is take the distance from our position target, which is our extension, and multiply it by the strength, and that will give you the force with which you need to pull this constraint back together. And that's what's going on. So why is it oscillating? That is the second question here. Well, actually, funnily enough, it turns out that something called a harmonic oscillator has exactly this same equation, that the force is equal to the negative extension, basically. And the reason this is interesting is because basically force is related to acceleration when you look at it, and because force basically is mass times acceleration, if you remember your physics. And so this is basically saying that the further away you get, the more you're going to accelerate towards the middle, and this creates this kind of sinusoidal wave that we're seeing over here. You don't have to work out the maths, you can take it for granted at this point. But basically, you end up with this sinusoidal wave over time of motion going up and down. Great. However, if you were to have this on a car, it would look really silly, wouldn't it? You would have those really bouncy cars that sometimes you see the cool kids going around in that just seem to bounce up and down all the time. Well, this is because in cars we have something called damping as well. We don't just have simple harmonic oscillation, we have damped harmonic oscillation. Now, what this adds to the equation, other than this kx term, there is a new term. You can forget about this fx term here. The new term here is the c multiplied by dx by dt. Now, dx by dt is the velocity, so you can just read that as the velocity, and c is a constant. So what we've got here is something else saying when you've got some velocity going on, try and apply a force against it. That's essentially a sort of friction type force, basically saying that if you are going fast, try and slow down. And what this leads to is this kind of thing. So if the dark blue here is an undamped oscillation, you can see it keeps going back to the same height and the same low all the time. When you've got damped motion, however, you start to get something like this green line where it oscillates a bit but then slowly dies away. And the red line is less and less oscillation before it dies away, and that is the result of more and more damping. So how do we apply damping with these springs that we're creating with our physics constraint? Well, that is done using velocity drive, or here in the linear motor where we have the velocity target. So we've got the same basic setup, and I can enable the Z, and basically that's a target velocity. So anything that deviates from the velocity of 0 will be basically used as the velocity in this term here, and it will be applied as a force back to the spring. So I might need to increase the strength here to be kind of similar to our strength of the position drive. I'm going to put it towards 20. It usually needs to be a little bit less. And we can go ahead and hit play and see what happens now. So hopefully it won't oscillate as much. You can see that it's coming to rest around a fixed point gradually, but it's coming there. And that's really good. So what we've got ourselves now is this position target and velocity target, and basically their strengths, which emulate the harmonic oscillator. Their strength being K for the linear and C for velocity, for the position, sorry, and for the velocity. Okay, so I'm going to present you with a challenge now to make a suspension using this spring. Not a suspension with a wheel, just the suspension on its own. So to make a suspension, here are the requirements you're going to have. So you're going to need a mass attached to the wheel. Obviously the mass is going to be suspended above the wheel. Both should simulate physics now because you want the mass to drop and the wheel to hold it up when it hits the ground. Then you want to tweak the strength of the springs so that it kind of behaves nicely and that the damping works properly and looks kind of like a suspension. And what happens if you tweak the masses of both of the objects in question, the mass and the wheel? What is going to happen? What's it look like is happening? And see if you can sort of explain it to yourself. Don't worry if you can't, because I will explain it after the challenge. So pause the video and have a go at building this suspension. Okay, welcome back. So let's start off. I'm going to rename these objects. The top one I'm going to call the mass. I'm going to copy the name so that I can put it into the physics constraint, because unfortunately they are name referenced, which is not very nice. Then we are going to rename mesh B to be the wheel, like so, and I'm going to copy that as well and take that over into the physics constraint. And sure enough, I'm going to put it into the component name 2 down here. So they should still be connected to one another. Now our mass is going to go on top, and I'm actually going to make it the root of our component, because this way it's going to be just a lot easier to manipulate it in the scene. I can pick up the mass and drop it again, so we can try multiple experiments. I'm going to reset the position of the physics constraint and the wheel, so that then I can just bring my wheel down underneath the mass. Okay, so that should sort of work. Let's go ahead and hit play. Okay, that seems to be just resting there. Well, it will just rest there because the mass I didn't set simulate physics on. They both need to have set simulate physics, and they will just drop on down. Now what's going on here is that when you set simulate physics on an object, it actually kind of pops it out of the hierarchy and goes into its own physics system of its own. So basically whatever you do, if you update the position of something, that one of these components, their child components, aren't going to be affected because they're no longer part of that same hierarchy. That's just a little bit of a side. So you can see that our suspension seems to be working out quite nicely. Maybe let's drop it from a higher distance and see what happens. So I'm going to lift it up a little bit higher, hit play. Okay, so yep, seems to be suspending and absorbing that shock. fairly nicely. Let's have a look. What else did I say? So we can tweak the strength of the spring, but maybe one way that we want to do this first is to go ahead and change the masses to be more representative of our tank. Okay, so here we've got the mass of the top. We want to go down to the physics section, enable mass in kilograms, and I believe the tank's mass is around, let's say, 10 tons, I think. And then we're going to go down to the wheel and we're going to enable its mass. What would the mass, sensible mass of a wheel be? Maybe 100 kilograms, something like that. So let's go ahead and save that and hit play. Okay. Okay, so that's kind of exploded. Maybe that's because I don't have enough strength in my spring. So that would make logical sense, wouldn't it? So let's go ahead and add more strength to the spring. I've just done that by a factor of 100. Let's see if that helped at all. Okay, that seems to have helped quite considerably, and what we've got here is a bit too much of a bouncy spring, so we do want to add basically more damping as well. So I'll change the damping by a factor of 102. Go ahead and hit play. Okay, and that has damped nicely, so we've got ourselves a nice suspension and nice spring. And you can see that changing the mass has had some impact, but not a whole heck of a lot. But what I do want to say is that mass seems to have a relative effect when it comes to springs. So usually if you add a bigger mass, it is going to compress the spring more and you'd have to increase the strength. Now that's not necessarily the case when it comes to physics springs in Unreal, as we put them together with physics constraints. What actually seems to matter is the relative difference, the relative size of the masses, because what I can go ahead and do is I can remove a factor of 100 from the wheel and a factor of 100 from the sprung mass. And if we go ahead and hit play now, it reacts in exactly the same way as it did before. So what we're seeing here is that the relative difference is what matters. So if I change this to the top mass to 10 but don't change the wheel, now previously it was 100 times heavier, now it's going to be just 10 times heavier. If I go ahead and hit play with that, what's going to happen? You notice that the strength is suddenly way more impactful, that suddenly the mass is staying exactly put. Now, one thing I want to raise here is a slight concern that if you use masses that are too different, probably more than 100 times different, you're going to get instabilities in the physics engine. That's just because of the limits of calculating physics in real time. So if I went for 1,000 times heavier on the top, let's see what happens. Let's go ahead and hit play. There you go. That's a perfect example of instability. The cube underneath, the wheel cube, just went and shot straight through the floor. Now you can improve matters a little bit for yourself, and let me just show you how. So let's go back to our 100 example. And for me it's working just fine, but for some of you it might not work as well. One of the reasons for this is frame rate. So I'm running at quite a high frame rate, but I can reduce the frame rate by going in to play, then hitting the key underneath the escape key to bring up the command terminal when I've got the main window focused, the game window focused. And I can do T.max FPS, and I can tab complete this, and I can set the max FPS to 30. And what you see here is suddenly the cubes start dancing around like crazy. Now the reason for this is that suddenly the simulation time step for physics has gone up, and so our simulation is just less accurate. So one thing that you might want to do, if you want large differences in mass like this, which is a question you can ask yourself in any game that you're building. So I could solve this problem by just saying, okay, the max difference of mass that I'm going to have is times 10. And if I go ahead and hit play with a times 10 mass difference, okay, no instability there. But if I go for 100 difference and I'm playing at 30 frames per second, I go ahead and hit play, and it's going to just not be happy. So if we go ahead to our settings, project settings, and go over to, let's see, to the physics settings, so engine physics, and go down to the section that says frame rate, you can see here that part of the problem is the maximum physics delta is actually quite high. So what we can do is we can enable something called substepping, which is going to say on every frame I'm going to run multiple iterations of physics, and that should hopefully stabilize our physics simulation. So if I go ahead and hit play now, with substepping enabled, you can see it's working just as well as before, even though my frame rate is down at 30 frames per second. This is a great way of making sure that your physics will stay consistent even when you run on a variety of different hardwares. So that is just a little thing to go and add to your project, especially if you've been seeing instability with your suspension. Hopefully that has been helpful. In the next lecture, we are going to be looking at attaching this suspension to our tank, and I'll see you there.